And we're back. Today we will continue on and complete our discussion of kernels. But before we begin, let's take care of some administrative bits. So written exam number 2, it is on the blackboard. It consists of reading a research paper and putting together a 30-minute PowerPoint presentation. And you'll be both giving this presentation in class half an hour each. The slides are due Tuesday, 21st of April 2020 at 4:30 p.m. Please note this down. This is not the usual 11:59 seconds. It will be at the beginning of class time on Tuesday, 4:30 p.m. So I will host the WebEx meeting, and during that WebEx meeting, give the presentation to each of you, give you up to a half an hour, and you'll both be giving the presentation. Okay, so where we last left off, we talked about final best hypothesis using a kernel, and we said that it's the same machinery, but you need this definition of the inner product in this feature space, Z, and that inner product is implemented by the kernel. And so when you get the final best hypothesis in Z space, signed W transpose Z plus B, well, that W is defined as a result from the primal formulation. We make that substitution, and we get an inner product between Zn and the x and the phi of x, which is the input parameter to the final best hypothesis. This gives us an inner product Zn transpose times Z. And so we need the kernel for the final best hypothesis, and we also need the kernel in solving for what B is. We choose any support vector in Z space, and we then solve. So this is where we left off, and let's continue on. So how are we really sure that Z exists? Because remember, in order for a kernel to be a valid kernel, some Z space must exist for which the kernel computes the inner product in that Z space. And so you could certainly do this by construction, and we did that when we talked about the example for the polynomial kernel degree 2. And we showed directly that a direct vector in Z space exists such that when you take the inner product, it computes the same expression as the result of what that kernel function was. Another approach for proving or demonstrating that a kernel is valid, that Z really exists, is using a set of mathematical properties, so-called Mercer's conditions, and we'll talk about that. And the interesting part about these mathematical properties is that people have gone off and proven that kernels with these Mercer's conditions are valid kernels, and moreover, certain combinations or transformations on these kernels, if you can show that it's a Mercer's kernel, they are also Mercer's kernels. This kind of closure under Mercer's conditions, as it were. So once you show that something is a Mercer's kernel, affine transformations of Mercer's kernels are also Mercer kernels. Likewise, if you have two Mercer's kernels and you compute the product of two Mercer's kernels, the result is also a Mercer's kernel. So once you show Mercer's kernels, there's certain closure properties under Mercer's kernels conditions that exist. And so we'll talk about what these Mercer's conditions are. And as if you satisfy Mercer's conditions, you're a valid kernel, and you also adhere to certain closure properties. Okay, and there's a carefree method, which is a little bit reckless, but you just kind of go through the machinery, define a kernel, and assume it works. See what happens. Good things can happen sometimes bad things happen. Okay, so let's take a look at your own kernel, Mercer's conditions. And so a kernel function is valid if and only if A, the kernel function is symmetric, because inner product is symmetric. If you take Z and Z prime, Z transpose Z prime and Z prime transpose Z should return the same value, so it should be symmetric. And also, the following matrix, the so-called Gram matrix, is positive semi-definite. And what that means is that all linear combinations of possible evaluations of your kernel function on all of your in-sample points, combinations of them, that matrix of evaluations of the kernel function is positive semi-definite. That means all linear combinations of the Gram matrix is greater than or equal to 0. Now, this Gram matrix, if you think about it, for any of your in-sample points, x1 through xn, what it corresponds to is effectively an outer product between all the z vectors that you get from these x input vectors and all the other z vectors, your z primes. So this Gram matrix is effectively an evaluation of your kernel pairwise over all data points. And this is the same as doing the outer product among all the corresponding z vectors in feature space. Okay. And so these two properties, your kernel is valid if it's symmetric, and your Gram matrix is positive semi-definite. Okay, so let's transition on to so-called soft margins. Now, let's go back to this idea of non-linearly separable data sets. So here we have a feature space in 2 dimensions, and we have our plus side of the line. Let's call this our negative examples, the red x's, and let's call this the positive examples, the plus side of the line. Now, in this example, it's slightly nonlinearly separable. Here we have an outlier. Here we have an outlier. And if we were to actually use a nonlinear hyperplane by mapping to z-space, we'd spend a lot of degrees of freedom trying to bend and fold and twist to accommodate that one or relatively small number of outliers. So we'd have a highly nonlinear hyperplane just for the sake of trying to accommodate 1, 2 points that are misclassified. Now you might say, gosh, well, let me just kind of deal with the fact that I'm going to get a few errors and En is going to be a little bit bigger than 0. But if you do that, well, you sacrifice En for the sake of generalization out of sample. And as you can see here, when we have this linear hyperplane ignoring those 2 outlier points, we get very good out-of-sample performance. Whereas if we spend that extra set of degrees of freedom, that nonlinearity, to pursue these 2 outliers, this red X and that blue circle, we see that our out-of-sample error is much larger because this is out-of-sample error, the blue here, and this is out-of-sample error, this red region. And so in slightly nonlinear problems, we want to sacrifice En because we don't want to spend extra degrees of freedom, nonlinearity, in our final best hypothesis to pursue the relatively small number of outliers. Whereas if we have a drastically nonlinear problem, we want to spend that complexity, and that's where kernels come into play. Kernels deal well with this type of data set, this geometry in your data set. But if you have something that's slightly nonlinear, you don't want to pay that cost. You want to just ignore, if you will, those small number of outliers. And so the so-called soft margins deal with this slightly nonlinear version of the problem. And to complete our conversation on support vector machines, we're going to combine both of these to complete our support vector formulation in talking about kernels. Okay, so we talked about the idea of margin points, and we had a constraint in our original formulation before we posed the Lagrangian, the primal form, and we talked about this expression, which was a way of talking about getting the classifications correct. And we converted this to equality form as an equality constraint, and we multiply it by a Lagrange multiplier, and we had the expression alpha n times yn W transpose xn plus b minus 1 is equal to 0. And we called this expression the so-called slack. And we modulated that slack to take care of the greater than part of this inequality when we convert to an equality constraint by this Lagrange variable. And we said that this Lagrange variable effectively absorbed that extra slack associated with the off-margin points so that we can change this to an equality constraint. Okay, so now what we want to do is if we think about what happens for a slightly nonlinear problem, we're going to talk about this idea called a margin violation. So here we have a linear hyperplane here. This is our hyperplane, and we have our margin points here. This red point, that's an on margin point. That's an on margin point. That's an on margin point. Now let's take this other blue point. Now if you're on the margin, you satisfy the slack is equal to 0. Now if you are off margin, well, let's push this point further in, and this arrow here, that red arrow, is a margin violation. Now this margin violation, if that margin violation is exactly equal to 1, that means this point is right on the hyperplane. If that margin violation is bigger than 1, that means it's misclassified. That blue point would come here on the opposite side, and that margin violation would be much bigger. And so we talk about margin points as being associated with satisfying this inequality, right? And we said the interior points are those points for which their greater than part is true. Now we need to account for the fact if you have a margin violation, you're in this direction, closer to the margin, you can even cross the margin, meaning you're misclassified. We need to account for that violation. So what does this do? This violation subtracts from that on-margin case. For the on-margin case, we refer to equality, equals 1. So if you're closer and closer to the margin, your margin violation, that means we need this extra term that's going to subtract from the equals 1 case. And we call that a so-called slack variable, and its Greek letter xi. Okay, that's how you pronounce it, xi. Now, xi is going to be greater than or equal to 0. If you are a margin point, xi is equal to 0. Okay, so that's just the equals 1. If xi is greater than 0, that means you're a so-called margin violation. You're in this margin. Within the margin, you've violated it. Now, if xi is exactly 1, that's equal to 0. Well, for which those points for which this is equal to 0, that's exactly on the hyperplane. If xi is greater than 1, okay, you're going to be across the hyperplane. That means you're going to be misclassified. So we're going to introduce this slack variable xi, which is going to be used to absorb the margin violation so that we can now include this expression, this modified constraint, in our optimization to account for those slightly nonlinear problems. And if you look at it in this previous slide, well, this x is really just a margin violation where xi was greater than 1. It's on the other side of the hyperplane, and that's the amount of the margin violation here. Likewise, this blue point, well, it has a margin violation that where xi is greater than 1. So if we consider the margin here, it's a very small margin. Not only is it over the hyperplane, it's really far over the hyperplane, so xi in that case is much greater than 1. So this xi is used to absorb the margin violations so that we can still express this constraint in the support vector formulation. And what we'll find is that a lot of things are going to drop out very nicely, and it's going to result in one change. And so here, the goal then is not just to look at one margin violation for one data point, xn. We're going to look at all the margin violations, and we want to choose the hyperplane that minimizes the number of margin violations, that total. And again, this is for slightly nonlinear problems. So we want to make sure, or slightly nonlinear data sets, we want to make sure that the total margin violation is very small. So we're going to include this sum for n goes from 1 to big N of all the xi n's, and we're going to include that in our optimization to favor solutions that include getting the classification correct with a small number of margin violations, allowing for that. So we incorporate the max margin criteria, getting the labels correct, this constraint, but we also include margin violations, these xi n's. Okay, so let's take a look at the optimization, this so-called optimization with soft margins. So here, this expression in this minimization problem, that says maximize the margin. So choose hyperplanes that maximize the margin. Okay, but we also want to control for the minimization of the total margin violations. Margin violations. Okay, so that's what this term does. And now we introduce this term C. That's a soft constraint. Now, depending on the size of C, if C is very large, that means we are saying in our optimization, maximize the margin, but don't allow for very many margin violations because it's going to penalize quite a bit if you have any margin violations. If C is very small, well, it says I'm going to allow for a lot of margin violations, so it's not going to hurt the optimization as much with this penalty term if C is very small. So it's going to be very generous with margin violations. And so this acts just like a regularization parameter, this C. In fact, it is a regularization parameter. It's saying I want to add this soft constraint, this C, that's going to allow me to modulate, increase or decrease the total margin violations that I'm going to allow when I choose my W's, my hyperplane. Now, of course, we have our constraint, and we modified our constraint to include margin violations, subject to getting the classification correct, including for margin violations with that getting the classification correct. So effectively, you're designating points as being margin points that have some margin violation associated with them. Now, these margin slack variables, psi n's, they're all going to be greater than or equal to 0. Now, the important part here is that you're penalizing for margin violations, but you're not rewarding for non-margin violations. And what that means is one way you could choose a maximum hyperplane is not by taking these points and allowing margin violations. You could kind of take these interior points and push them further away, or these margin points and push them further away. That would be rewarding for margin violations in a particular direction. But we're not going to do that. We only want to take some of those margin points and allow for violations in this direction going towards the hyperplane. So these psi n's are going to be greater than or equal to 0. And so our weight vector is in d dimensions as before. Our bias term is in real valued scalar, and xi's are going to be with n of these xi's, right? So we're going to have a vector of big N many xi's. So xi is going to be equal to xi1 up to and including xi big N. And we have n many of them because we're going to have a particular slack variable for each of our in-sample data points, of which there are big N many. Okay, so we have these constraints, and now we'll form the primal problem using this modified set of constraints, including this penalty term. And when we form that, you'll notice there's an inequality constraint. So we're going to make it a 0 constraint by subtracting this term from both sides of the inequality. And when we do that, that's going to give us yn W transpose xn plus b minus 1 plus psi n is greater than or equal to 0. Okay. So then we're going to take this expression, and now, like we did before, we're going to absorb that greater than part of the inequality for the 0 constraint with alpha n, and then we're going to write that same expression equals to 0, and we're going to include that in our optimization. Okay, so let's take a look at this. And we also have our psi n's greater than or equal to 0. Okay, so let's take a look at our newly formed Lagrangian. So we have maximizing the margin, max margin. And recall, this is a minimization problem, so this is our new primal problem. And it's a function of W, B, our xi's, alpha, and beta. Now, this primal problem is going to be a minimization problem, and we're going to solve this by setting the gradient with respect to some of these variables equal to 0. Okay, so we have the max margin, and then here we're saying minimize the number of margin violations, and here we want to, in this constraint here, we're expressing getting the classifications right. Okay, getting the classifications right, allotting for margin violations. Okay, so there are margin violations. So it's our modified slack plus the margin violation modulated as an equality constraint with our alpha n's. And then we say minus because we want this to be as small as possible, right? So we want to have getting the classifications correct, as many of these as possible to be correct, right? So we say negative here because this is a minimization problem. We want this to be as big as possible, accounting for margin violations. And then this last constraint here, we had psi greater than equal to 0, right? And so if psi is greater than equal to 0, we sum them together. If we sum them together, well, we include the negation of this that says try to make these margin violations, these psi's, as small as possible. You want to have as few of them as you can. Okay, so here, this third term here, if your psi n is in the previous slide, if your psi n in the previous slide, oops, where is it? If your psi n, here we have, if your psi n in this previous slide is greater than or equal to 0, well, remember, psi n is your margin violation. If psi n is equal to 0, that's a margin point, and you want to have as few margin violations as possible. So if that's the case, we can take these psi n's, we add up all the total margin violations across the entire data set, and then we can set that as an equality constraint equal to 0. And when we say we sum these up, sum of all the psi n's summed up for n goes from 1 to big N, that's going to be greater than or equal to 0. So now if we change this into an equality constraint equals 0, we absorb this with another Lagrange variable, and we're going to call that b. So we have a bn for each one of these psi n's. So if we add that second Lagrange variable, this is a second Lagrange variable, and the purpose of the second Lagrange variable is to absorb that equals part of that greater than equals to 0 for the psi n's constraint. We include that with a negation because we want this expression to be as small as possible. All right. So here we have this other part that enforces the psi n's being greater than or equal to 0. Okay. And we want that to be as small as possible because we want to have these margin violations be as small as possible. Okay. If these psi n's are larger than 0, okay, what's going to happen? If they're larger than 0, we're going to allot for our margin violations. So this is just the equality version of our psi n greater than or equal to 0 as a constraint. Okay. So here, the primal formulation, we're going to minimize, because remember it's a saddle point we're solving for. We're going to minimize with respect to W, weight vector, B, or bias, and psi, our slack variable that controls the margin violation. And this regularization parameter C, this soft constraint, is going to tell us how aggressively we're going to allow for these margin violations. If C is large, we're going to allow for very few margin violations. If C is small, we're going to allow for a large number of margin violations. And this says get the classification correct, including margin violations. And this says the margin violations are greater than or equal to 0. All right. So we're going to minimize this to W, B, and psi. And then we're going to take that solution, substitute it back to the Lagrangian, and we're going to maximize with respect to our Lagrange variables with the alphas as well as the betas. So let's solve the first problem. If we set the gradient with respect to W equal to 0, well, we're going to have this term. That's going to be W, because we have, like saying W squared here, 2 times W, the derivative of W squared, so that's 2 times 1/2 times W. And this doesn't involve W, so that drops out. This drops out, this drops out, this drops out. And the only thing that's really left here is that part of the summation that includes the alpha n, yn, W transpose xn. So here, if we do that, we have, guess what? The same thing we had before before we included margin violations, we have a definition for W. W equals the weighted sum of alpha n, y, and xn. If we do the gradient of the primal problem of Lagrangian with respect to b, set it equal to 0, well, the only term that has a b here is this alpha n, y, and b, and that's going to give us this expression that we had before, which will result in a constraint, the sum, n goes from 1 to big N of alpha n, y, n is equal to 0. So then lastly, if we take the gradient with respect to psi, if we look at this, we have three terms in a sum. We have this term, c times the sum of all the psi n's, okay. And then we have this term. We have alpha n times this psi n underneath that summation. And then we also have this minus beta n psi n. So if we take the gradient with respect to each one of the psi n's, only one term from each of these sums counts. And we have a c times psi n. We have an alpha times psi n, minus alpha times psi n. And then we have a minus beta n times psi n. So if we have psi n raised to the 1 power in each of those, and we're putting that c times psi minus alpha n times psi n minus beta n times psi n, well, that gradient with respect to psi n is going to be c minus alpha n minus beta n, instead of equal to 0, equals 0. So this third quantity gives us a constraint on alpha n. Now, if this beta n as a Lagrange variable is greater than or equal to 0, that means the biggest that alpha n can be is equal to c, right? Because this is greater than or equal to 0. Alpha n, in order for this constraint to be true, c minus alpha n minus beta n, in order for that to equal to 0, well, if this is greater than or equal to 0, that means alpha n, the maximum alpha n can be, alpha n, has to be less than or equal to c. And that's going to be an upper bound on what this alpha n can be, right? So it can be less than c, it can be less than equal to c, in order for this to remain true if beta n is greater than or equal to 0. Okay, so we take that and then we substitute. And if we substitute back in, we find that a lot of things are going to drop out. And they're going to drop out because of this term. Now here we see some summations, and we're going to see a summation of something that involves a psi n. We're going to have this term of the sum. We're going to have this term of the sum that has the alpha n and the psi n, right? If we distribute this multiplication of alpha and then we group together all the sums separately, and then we're going to have this beta. So that, because of this constraint, is going to sum to 0, right? We can factor out a psi n, and if we put those terms together, we're going to have a psi n times c minus alpha n minus beta n, for n goes from 1 to big N, right? So you're basically going to group this term with this term times the psi n with that term, right? And if you do that, everything drops out and you're left with the same dual formulation that you had from before when we solved the original primal problem without the margin violations. But the one artifact that remains is our constraint on alpha. So before we said that alpha is greater than 0, the alpha n's, and so there was no upper bound on alpha. The upper bound was infinity. Okay, and so with this constraint, the c minus alpha n minus beta n is equal to 0. That sets this upper bound, and the only thing that's changed with this margin violation added to the support vector formulation, the only thing that's changed is that we now have this upper bound of c, that upper bound on our alpha n. Okay, and this is for every single alpha n, alpha 1, alpha 2, alpha 3, up to and including alpha big N. Because remember, there's an alpha Lagrange multiplier associated with every single in-sample point that we trained on. All right, so from this, we get a definition for W, as we said before, and we can identify our support vectors as we did before. And this is going to minimize the expression for our objective, 1/2 W transpose W. That, again, is the max margin, with a penalty that talks about the margin violations. And so C is going to control how much margin violation you can have. Okay. And so the only difference between the margin violation version of the support vector formulation and the non-margin violation, hard margin as it's called, formulation is this upper bound on our Lagrange variable alpha, the alpha ends. Okay. So let's take a look at this. So you have two types of support vectors. You have what are called margin support vectors. Those are margin support vectors where alpha is greater than 0, but it's also greater than C. Those are support vectors that are right on the margin, such as these. Right? Then you also have what are called non-margin support vectors. Those are support vectors that include margin violations. That's this one. So now you lump your support vectors into two categories. You have margin support vectors and non-margin support vectors. The margin support vectors also have a slack of psi equals 0, right? Because remember, we said yn W transpose xn plus b is greater than equal to 1 when we said minus psi n. So if you are a margin point, psi n is going to be 0, right? And you're going to have the equals 1, equality version, and those were the points that we defined as being the on-margin points. But the non-margin points, those margin violating points, those are going to have your psi n, that's going to be greater than 0, right? Because this psi n represents the amount of margin violation. And consequently, for those non-margin support vectors, those are going to have an alpha that's equal to C. So here we have alpha less than C. Here we have alpha, the Lagrange multiplier, for that on-margin point, or that margin violating point. Alpha n is equal to C. Okay. So for this case, we have this expression, yn W transpose xn plus b is less than 1, right? Because if it's less than 1, because you're subtracting off this psi n. If you're on the margin, it's equal to 1, so it has to be less than 1. Because this psi n, it strives to actually subtract from that 1 to give that expression less than. So these are the non-margin support vectors. Okay. So as long as you violate the margin, you're still a support vector, but you're just not a clean support vector. So here we have a margin violation, and you can violate the margin so much that you're completely on the other side of the hyperplane, and you're now misclassified. Okay. And so here, this margin violation can account for misclassified points. And again, the whole purpose of soft margins is so that you can work on data sets that are only slightly nonlinear without spending the cost in nonlinearity in feature space to try to chase after a small number of points. You're sacrificing in-sample error. So as long as you violate the margin, you're considered a support vector. You're just not a clean support vector. You're a so-called non-margin support vector. Your psi n is greater than 0. Okay, so that's all I had to say, and this completes our conversation about support vector machines and the full-blown treatment of support vector machine. It has a nonlinear kernel, so you define an inner product that using the kernel trick, you benefit from nonlinearity, but you reduce your dimensionality to just the number of support vectors. And so you can draw highly nonlinear decision boundaries without paying the cost of that feature space dimensionality. And then you also allow for margin violations so that you can sacrifice in-sample error and not spend nonlinearity pursuing a relatively small number of margin violations, which includes misclassified points. So with that, that completes our module on support vector machines, and that's the full treatment, our so-called soft margin support vector machine. And we will end there. I look forward to your written exam number 2, your presentations on Tuesday. I will see you on Tuesday.